I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this lecture series, we are going to see the topic called Method of Images for the unit Dielectrics and Steady Electric Current. So, can you guess the topic by seeing the figure? So, there is a tree and its image. Yes, the topic is the method of images. One important characteristics of the dipole field is the infinite plane at zero potential that exists midway between the charges. Such a plane may be represented by a very thin conducting plane that is infinite in extent. The conductor is an equipotential surface at a potential V is equal to 0, and therefore electric field intensity is normal to the surface. So what we do is we can easily replace the dipole configuration as in the diagram in the next slide, the first diagram, with a single charge and a conducting plane as in the second diagram. So in the diagram you can observe there is an equipotential surface at V is equal to 0, and we have two charges with the conducting plane, one is plus Q and another one is minus Q. So the same diagram according to the method of images is replaced with only one charge above the conducting plane plus Q. And according to the method of images, the fields in the upper half of each figure is 0. Below the conducting plane, we might also substitute a single negative charge to obtain a dipole arrangement and obtain equivalence of the fields in the lower half of each region. We know that dipole is a separation it is a conductor which is having the separation of d meters, and at two ends it is having the same charge but of opposite sign. So this is the dipole arrangement. So in a single charge in the above the perfectly conducting plane, we maintain the same fields above the plane by removing the plane and locating a negative charge which is at a symmetrical location below to that plane. So this charge is called the method of the original charge, and it is the negative of that value. So any charge configuration above an infinite ground plane may be replaced by an arrangement composed of the given charge configuration and its image and no conducting plane. So this is the method of images. So in the diagram you can identify there is a line charge distribution with line charge density rho L above the conducting plane, V is equal to 0 in diagram 1. And according to the method of images, in the diagram 2, the conducting plane is replaced and the equipotentials below the equipotential surface V is equal to 0 at the same symmetrical location, but below to the surface it is the negative of the previous charge distribution is substituted. The negative of the previous charge distribution is minus rho L is the line charge density. So in this diagram, total field is obtained by adding the fields due to both the charge distributions, both the positive charge which is above the equipotential surface and the negative charge below the equipotential surface. So this can be explained by the by an example. So in the example, they asked to find out using the method of images and the surface charge density at point P of 2, 5, 0 on the conducting plane Z is equal to 0, and the line charge is given 30 nanocoulombs per meter located at x equal to 0 and Z equal to 3, and if we remove the plane and install an image of the line charge minus 30 nanocoulomb per meter at the symmetrical location, that is x equal to 0 and Z equal to minus 3. So that will be given in this next slide. The field at point P, that is P of 2, 5, 0 can be obtained by superposition of the two fields of the line charges, the positive line charge and the negative line charge, and by adding these two we get the total charge. So here the radial vector from the positive line charge P is r plus equal to 2ax minus 3az, and r minus is equal to 2ax plus 3az. So the individual fields are adding the two fields. So in the first diagram we have a conducting plane with a single charge 30 nanocoulombs per meter. We want to find out the total field at p of 2 comma 3 comma 0. So by using method of images, what we do is we will remove the conducting plane and we locate the negative of the given charge at the symmetrical location below to the reference point. So we have minus 30 nanocoulombs per meter. So at point P, in order to find out the total electric field intensity, we adding the two fields due to the two charges, and we get the total field. So this is the method of finding the total field for a dipole. References. Thank you.